Hi, welcome to our pre-calculus. The topic today is half-angle identities, problem type 1, degrees. So let's go ahead, take a look at the kind of problems we are going to be solving today. It's first one is calculate the exact value of sine of 22 and a half. What is so special about 22 and a half? It's half of 45, and 45 degrees is in the list of our famous angles. We know everything about 45 degrees, and what we are going to discover today is that if you know an angle, then you are going to know everything about half of that angle, meaning you can write expressions for sine, cosine, tangent, and so on. Interesting piece of trivia about this problem is that the ancients, meaning mathematicians of 2500 years ago, used this idea to come up with the approximate value of pi. So everybody had been fascinated with this concept of pi, ratio of perimeter of a circle to its diameter. And one way to approximate it is by fitting a polygon inside the circle, like a square, an octagon, and so on. When you go from square to an octagon, what do? Let me draw the picture here to motivate the topic. So if you have a circle, you want to approximate it. A very rough approximation for this is to say, well, its perimeter is close to the perimeter of this square. That's very rough, but you can always improve that. So how do I improve it? I subdivide each of these arcs into two, so that is a half angle idea. So I'm taking each of these angles and dividing it in half. Now by now the red octagon is much closer to the circle than the square was. And then say, well, I can improve this thing. If one level is good, then the two level is better. I go and subdivide this one. By now you cannot even see that I am subdividing it. So take each of these and make, instead of octagon, make something with 16 sides. So that's what the ancient did. They kept subdividing it, and imagine doing this thing without a calculator. They went through 5-6 levels of subdivision to come up with good approximations for pi. So way of calculating pi all the way to 1600 was this idea of half angle identity. And then at that time Isaac Newton came up with a much faster way of doing that. You're going to learn about that in your calculus classes. So interesting bit of history with respect to pi. And where does our lecture start from? We have already seen double angle formulas. Let's just look at two of them. Cosine of 2a. We had two versions of it, well, actually three versions of it. But in terms of one function on the right hand side, these two stood out. Cosine of 2a was either 2 cosine square of a minus 1 or 1 minus 2 sine square of a. Slight rearrangement we did in the previous lecture, we call that power reducing formula. We put cosine square or sine square on one side and cosine of 2a on the other side. Okay, from here we just need one step. To go to our next level, which is just take a square root. So we'll have cosine of a. No, cosine of a could have been positive or negative, so that has to be determined. So that's why we have a plus or minus. And we have some radical of whatever is on the right hand side. And same way, sine of a is plus or minus similar 1 minus cosine of 2a over 2. And well, how about tangent? Well, tangent, you can take it out of the ratio of these two. So tangent of a, ratio of sine to cosine. We still don't know what plus or minus applies to what other plus or minus. So it's not that the plus goes with plus and minus with minus. It's all depends on what quadrant angle A is in. So we still have a plus or minus here, which is the ratio of these two, 1 minus cosine of 2a over 1 plus cosine of 2a. So when I take this and divide it by that, the 2's cancel, and then I get a ratio of this numerator to that numerator. So sometimes these formulas are written in this style, and sometimes to insist that this is half of that one, they are written in slightly different form. That is, you could write it cosine of a over 2. So you see that you're taking half of something explicitly. Here is half of a, and then remember, this is twice the angle on the left, so now it becomes cosine of a over 2. And same way, sine of a over 2 is plus or minus 1 minus cosine of a over 2, and tangent of a over 2, then again is plus or minus 1 minus cosine of a to 1 plus cosine of a, and that takes care of it. So either this one or this one are called half angle identities. And an interesting twist to the story of formulas here is that now tangent has 3 formulas associated with it. You remember when we were doing double angle, cosine had 3 formulas. Now when it comes to half angle, actually tangent turns out to have 3 formulas to itself. And to introduce them, let me just quickly go through that. Say, for example, if you have tangent of a over 2, well, of course that is sine of a over 2 over cosine of a over 2. If I go ahead and multiply this thing by cosine, so I'll have sine of a over 2 cosine of a over 2 divided by, this is going to become cosine square of a over 2. Now I want to create sine and cosine of a itself, so I double this and double that one. What is the numerator? The numerator, 2 sine a cosine a, that is the double angle formula that gives us sine of a. Now cosine squared times 2 is going to give 1 plus cosine, so I will have 1 plus cosine of a. So if you rearrange this formula, 2 cosine square of a is 1 plus cosine of 2a. 2 cosine square of a over 2 is going to be 1 plus cosine of a. We can do another one similar to this, or rather twisted path to come to this particular formula. But what is important about it is that on the left hand side I have half the angle, on the right hand side I have the full angle. So here's another version of this. Tangent of a over 2, again I start with the same thing, sine of a over 2 over cosine of a over 2. This time I multiply numerator and denominator with sine, so this becomes sine square of a over 2 over cosine of a over 2 times sine of a over 2. So I multiply numerator and denominator with the same thing. Now I double denominator twice sine cosine, well, that is sine of double of this angle. 2 sine square 2 times sine square is 1 minus cosine of twice the angle. So it's 1 minus cosine of twice this angle, which is just A. So short end of this is two formulas we have. Let's write it cleanly on the side. Tangent of A over 2 is sine of A over 1 plus 1 plus cosine of A. Yeah, and then another one, tangent of A over 2 is 1 minus cosine of A over sine of A. Okay, so we went through the derivation of the formulas, and then now we are going to start with actual problems themselves. Those of you headed toward mathematics, theoretical engineering and such, you want to be able to follow what happened here. That is, you just don't want to use the formula, rather you want to be able to derive the formula. But either way, so let's go ahead and see what we are going to do. Before we start there, notice these are a little bit easier than that one, because we neither have the issue of taking square root, nor do we have the issue of trying to decide if I have to use plus or minus. So in some sense these are superior to that, but again, it's your choice which one of these formulas you want to use. If you have already found sine and cosine, taking the ratio of that bypasses all of these. Let's start with sine of, I want to find sine of 22.5 degrees. That is sine of 45 degrees divided by 2. And, well, that has to be from this formula. So there is a decision to be made. So decision, I put a plus or minus which one. Then radical 1 minus cosine of. So this is the numerator, just double of the angle on the left. So it's cosine of 45 over 2. Well, before going any further, 22.5 is in the first quadrant. Its sign definitely is positive. So this whole thing resolves to resolves to plus. So we know that obviously the sign we are looking for is positive. Sine of 22.5 is positive, so that's what we do. Then, well, now we say a cosine of 45. Do we remember what that one was? Hopefully we remember that it was radical 2 over 2. The whole thing divided by 2. So if you take common denominator, in the numerator you have 2 minus radical 2. 2 times 1 is 2. 2 times 2 is a 4. Comes out of this radical. Yeah, it becomes like that. Isn't that neat? A square root of 2 minus square root of 2, the whole thing divided by 2. So this is called the nested radical. Nested radical. And if you keep doing that, there will be more nesting. That will be, if you go next round, it's going to be 3 of these radicals on top of each other, and 4 and 5. And that is what the ancients did. They kept putting radical on the radical, and the calculations are not trivial at all. Imagine they had to do it by hand. There was no calculator there, and it can become quite a calculation. Okay, so we did this. That's the answer. How about next problem? Sine of 75. Sine of 75. What do we say about that? Well, you might say, I've seen sine of 75 before. We did this problem in the addition case. 75 was like 45 plus 30. Yes, you can do it like that. So if you said that, you are very alert and you say, okay, I did this problem once before, so I could use the addition formula. Yes, you can do that. Here we are practicing this version, which is, well, how about the half angle formula? So it's a sine of 75. So this is solution number one. You can go like that. Just to remind you, sine of 45 cosine of 30 plus cosine of 45 sine of 30, and then this was radical 2 over 2, radical 3 over 2, radical 2 over 2, 1 over 2, radical 6 plus radical 2 over 4. Now that's solution number one. Solution number two, what we are doing here is saying sine of 75 is same as sine of 150 over 2. Okay, that's 150 over 2, and that is, again, 75 is in the first quadrant, so the correct choice of plus or minus is plus, and then I have 1 minus cosine of this angle 150 over 2. Yeah, that's the same formula. Now the next question is, what was cosine of 150? Do we remember that one? Let's remind ourselves. Either you have to remember the whole table, or you have that circle pattern with all the numbers on it, or so we have 150. I want to do cosine of 150 and see if I remember how does this go. Well, we said cosine of 150 and cosine of 30 by using reflection identities. They are opposite signs of each other. Cosine of 150 is same as minus cosine of 30. So, and that's minus radical 3 over 2. Or look it up in your tables. That is more comfortable, but I insist that you try to do it this way. 1 minus, so it's minus radical 3 over 2, and the whole thing over 2. So 2 times 1 becomes 2, and then I have minus becomes plus, and then 2 times 2 becomes 4, comes out of the radical, becomes like this. Now we are facing a very interesting situation. We calculated this way, we got this answer. We calculated that way, we got that answer. And on the face of it, these two look very different. Are they really the same thing? And let's go ahead and investigate if they are the same or not. Okay, so we have a very interesting situation. Let me kind of accentuate this thing. We have one answer here, and previously we had this answer. And we stare at them, is how does one of these things equal to the other one? And that's an interesting problem. So many problems like this do show up in mathematics. Same numbers appears in two different styles. One way to see that these two numbers are the same, first of all, we pay attention they are both positive. If I square them and the result of squaring is the same, then the two numbers are the same. So here I go, like I say, radical 2 plus radical 3 over 2 squared. So by the way, what we are doing here is just out of our own curiosity. Either of these two will be correct answer and you can stop. But we are just trying to satisfy our own curiosity. Why is this looking like that? So square this thing. The radical comes out and you get 2 plus radical 3. Square of 2 is going to be 4. That's all we can think of doing there, so that's where it stops. How about this one? That one is a little bit more messy. Radical 6 plus radical 2 over 4, if I square it, I get square of the first one, which is 6, square of the second one, which is 2. Let me make a bit of space here, didn't imagine. Okay. So 6 and 2, and then twice the product, twice this and that one. 6 times 2 is 12. 4 squared is 16. Now 6 and 2 is 8. Radical 12, you can write it as radical 4 times 3, and that is 2 radical 3. So 2 comes out, times another 2 makes a 4 radical 3 over 16. Now factor 4 and simplify, divide numerator denominator by 4, so you get 2 plus radical 3 over 4, which is exactly this. So rather interesting magic there, that the two answers that you have, they are the same. In this case, a nested radical could be simplified. That is rare that it can be done. It's not always that a nested radical can be converted to sum of two radicals, but here it did happen. Okay, so that was one example. Here we have another one, cosine of 157.5. The question was, is cosine of 157.5. Well, if this wants to be done this way, we double this, so it becomes 315 degrees divided by 2. We look at this angle. Which quadrant is it in? 157, of course, somewhere in second quadrant. Well, what's the cosine of an angle in the second quadrant? It's going to be negative. So the choice is negative here. Radical. So for cosine, make a choice of the plus or minus, then 1 plus cosine of the angle. So I'll have 1 plus cosine of 315 degrees over whole thing over 2. Well, where is 315 degrees? 315 degrees, again, you either look it up in your circle on your table. You say 315 degrees, there's a big angle here, 315, and that is what is left here is 45 degrees. So 45, cosine of 45 and cosine of 315, by reflection identities, they are the same. Cosine of 315 and same as cosine of 45, which is just radical 2 over 2. So this becomes minus 1 plus radical 2 over 2 over another 2, minus radical 1 times 2 plus radical 2. 2 times 2 is 4, and comes out of this radical is a 2. So here's a nested radical with pluses. Okay. So that was cosine of 157, and this is going to be tangent of 112. Tangent of 112.5. Let's do this thing two ways. So we said, or maybe we wish 3 ways. Tangent is fruitful and it's multiplying. Has lots of different ways of dealing with tangent. Number 1, number 2, number 3. Let's see. First, we notice that this is tangent of 225 degrees, half of that. So what is special about 225? Well, first of all, 112 is somewhere here. 112. You will calculate that one. You are in the second quadrant, so this has to be negative. Then I'm going to write that first formula we had. 1 minus cosine of 225 over 1 plus cosine of 225. All right, let me just again remind you. Tangent of half of a is 1, sorry, jump. 1 minus cosine of a or 1 plus cosine of a. Choose plus or minus according to the quadrant of the angle you're calculating and the function you're calculating. So here we are making decision based on that angle, not the 225, based on somehow this screen is very sensitive. Okay, so based on 112, we know the tangent in second quadrant is negative, so that is start of the story. So I have minus radical 1 minus, now cosine of 225. Where is 225 itself? 225 is like this. 225 cosine of 225, notice this is just a 45-degree angle. So that's going to be minus cosine of 45, okay, by reflection identity, or look it up in your table. So 1 minus this is going to be minus radical 2 over 2. So 1 minus radical 2 over 2 is going to become 1 plus radical 2 over 2. The denominator is 1 minus radical 2 over 2. Then we multiply by 2 if you wish. So I'll have minus radical 2 plus radical 2. By the way, software will be happy with this one as well. But if you want to get ready for further stuff, okay, can we clean this up more? Yes, you can. So let's go ahead. I have minus radical 2 plus radical 2 over 2 minus radical 2. How do you simplify? Multiply by the conjugate, is that right? Remember the conjugate of the denominator to rationalize denominator. So it becomes 2 plus radical 2, 2 plus radical 2. So what's the advantage of this one? Notice what happens. When I multiply the denominators, 2 times 2 is 4. Radical times radical is 2. So that so I have a big radical. Inside of it, this times that, they're same. So I'm better off if I don't square, just write it, that whole thing squared. Denominator 4 minus 2 is 2, and I need to squeeze in a negative sign here. Next, I need notice that square in square root is going to come out, so minus 2 plus radical 2 over 2, and this is in the radical, so I write it as radical 2. Now I simplify. 2 divided by radical 2 is just radical 2. Radical 2 divided by radical 2 is 1. Now, wouldn't you say that this is a lot simpler than that mess or any of the other ones? So we simplified. We got tangent of 112.5 turned out to be minus radical 2 plus 1 quantity. So this is the simpler form of it. Once again, most software would not care all that much. I mean, it all depends if it asks you to simplify or not. So you try to see. This one doesn't insist that you simplify, but for your future, you do want to do this. Okay, plan B. Plan B was that we have plan A, B, and C. So plan A, sorry, A, B, C. Okay, let's try to use plan B. Tangent of A over 2 is sine over 1 plus cosine. Tangent of A over 2 is, so one form is sine of A over 1 plus cosine of A. So let's look at this as solution type B. So this one tells me tangent of 112.5 is sine of twice this, which is 225 over 1 plus cosine of 225. Okay, with double. Now sine of 225, sine of this is going to be minus radical 2 over 2. So cosine, same way, minus radical 2 over 2. We go ahead and multiply by 2. Okay, why is this same as everything I had over there? Let's go ahead and try to clean up. So I multiply by the conjugate. So minus radical 2 times 2 plus radical 2. When I multiply the conjugate, I get 4 minus 2. That's just 2. So now we have the following. Let's multiply radical 2 times 2 is minus 2 radical 2. Radical 2 times radical 2 is just a 2. And a minus, I will put a minus outside, divided by 2. Now cancel the 2's and you get, so 2's cancel and get a minus radical 2, and remember this is just a 1. So if we got the same answer, you can try another one. Solution type C, tangent of A over 2 is also 1 minus cosine of A divided by sine of A. So I leave that to you to go ahead and discover for yourself that you get the same answer. So here we got type B, tangent of 112.5. So I'm gonna leave that for you to go through the process and do the rationalization and find out the final answer is the same as everything we have done so far. Okay, so what did we do? Half angle identities, a whole bunch of them here. So we said it comes from the double angle identities that you had already. We already had the power reducing style of this thing. All that we are doing is taking square root. There's a plus or minus. That has to be decided based on the function and the angle that you're calculating at the start. That's what decides this. We had additional formulas instead of the tangent. Coming with this radical, we can have expressions without the radical, somewhat easier to use in some applications. Okay, until next time, when we are going to do exact same thing, but with radians. So until then, good luck and God bless.